What's up everybody, welcome to another video, and I hope you're ready to flex those brain muscles. In this video I'm going to talk about some common polar equations such as lines, circles, cardioids, Limacons, and roses. And what you're looking at right now are some notes that I actually made about polar equations and some strategies for graphing them. And I'll put the link to these in the description so you can download them, print them out, share them with your friends, do whatever you want to do. But essentially it's just a chart containing all of our different common polar equations and some information about them. Then I get into making note of some patterns and symmetries, some graphing strategies, and then closing remarks and a few examples. So I recommend checking these out. You might find them beneficial. But the goal for this video is not just to read off these notes, obviously. I don't want to just hand these out and say, here, memorize all this stuff. It's always better to try to understand rather than memorize. So that's the goal of this video. We're going to go through a bunch of different examples and see if we can build some understanding as to why some of these graphs look the way they do. So let's go ahead and start jumping into some examples. So one thing I'd like to point out before we get to our first example is that the polar coordinate system and the rectangular coordinate system line up pretty nicely. And I'll kind of explain what I mean by that right now. So just a reminder, in our polar coordinate system, we have a pole and then a polar axis, right? But what I like to do when I'm graphing in polar coordinates is draw a dotted line through the pole, directly vertical, right? And what this represents in polar coordinates is the line theta equals pi over 2. So if you see me refer to that in my notes, this is the line I'm talking about. But if we want to think in terms of rectangular coordinates, this is our y-axis, right? Just like our pole in terms of rectangular coordinates is our origin. And I can do a similar thing. I like to extend a dotted line here as well. And I often do this when graphing because it turns out that if I have an equation and it's in polar form and I sketch its graph, and then I take that same equation and convert it to rectangular form and sketch its graph, the two graphs look exactly the same. And if I sort of lay this pole and polar axis on top of the x and y axis, the graphs will literally be on top of each other as the same thing. So I want to point this out because sometimes it's helpful to think about the x and y axis because it's something we're kind of already familiar with. But not only that, sometimes it's really useful to convert a polar equation to rectangular form because it makes it more obvious of what the graph of that equation is going to look like, right? But we typically only want to do that conversion if it makes our lives easier or if it makes things make more sense. Once we get into cardioids, Limacons, roses, trying to convert those, I don't recommend it. It definitely doesn't help it make sense. It gets more complicated, right? So hopefully this makes sense. Let's go and jump into our first example. All right, so our first example here is this equation theta equals pi over 4. And where I see a lot of students get confused about this is they think, well, where's the r? There's no r. And they get kind of confused about that. So the way I tend to explain it is, well, we can write a plus 0r here, right? And that's the same equation. Essentially, no matter what I plug in for r, theta is pi over 4. And we've dealt with a similar situation like this in rectangular coordinates with equations like this, y equals 5. There's no x, but we still interpret this as no matter what x is, y is 5, right? So we can do a similar thing over here with this equation. So if I write plus 0r, it may help it make a little more sense. And this may help as well. Really what the graph of this equation will look like is all the points of the form r, comma, pi over 4, where r is any real number, right? So let's draw our pole and our polar axis and see if we can sketch this. So let's see, where is pi over 4? If I draw my vertical line through the pole, and if I start at the polar axis and open up to the line pi over 4, that's this line here, right? So I'm taking all of these points because r can be anything as long as the theta is pi over 4. And what this does is it forms a line. But here I've just taken the positive values for r. I need to include the negative ones as well. So the line actually intersects the pole. And the easiest way to graph equations of this type, where we have theta equals some angle, is just open up to the angle, plot a point there, intersect it with the pole, and then continue the line all the way through on both ends, right? So if you want to make more sense of why this is a line, we can even convert it to rectangular form by just taking the tangent of both sides. And this isn't necessary, but I think it is kind of cool to see what's going on here, right? We know that the tangent of pi over 4 is 1, and we know that tangent is y over x. So now if we multiply both sides by x, what we end up with is the line y equals x, which in the rectangular coordinate system, right, if I think of this as my x-axis here, and this is my y, it would look exactly like this. We have a line going through the origin with a slope of 1, right, which looks exactly like what we graphed. So we can confirm that our graph is correct. And another cool thing I'd like to point out is when I do this conversion, the slope of this line is 1, and where that 1 came from is the tangent of this angle. So that's something that is going to be consistent, is that the tangent of whatever angle we have here is always going to be the slope of our line if we decide to convert to rectangular coordinates. So there's our first example. I guess I'll just label this pi over 4. All right, let's go to our next example. All right, so here are our next couple of examples. We have the equation r sine theta equals 5 and r cosine theta equals 2. And the cool thing about these equations is that they're both practically begging for us to convert them to rectangular form, right? Because we know that r sine theta is equal to y. That's an equation we use to convert back and forth between rectangular and polar all the time. And that just comes from the definition of sine, by the way. Sine equals y over r, multiply both sides by r, you get y equals r sine theta, right? Similarly, x is equal to r cosine theta. So we've converted both of these to rectangular form, and now it's pretty clear as to what their graphs are going to look like. We're going to have two lines. This y equals 5 is going to be a horizontal line, and this x equals 2 is going to be a vertical line. So let's see if we can sketch these graphs. Draw my pole here, my polar axis. I'll draw a vertical line going through the pole. And now I'm going to go a distance of 5 away from the pole here. 1, 2, 3, 4, 5. And I'm going to extend this across, and this is going to be my graph. Extend this across. There we go. That horizontal line. Okay. Similarly, down here, I can draw a pole, polar axis. Let me do that a little better. I'm not the best at sketching beautiful looking graphs. Usually they don't look very beautiful, so I apologize. If you want beautiful graphs, use Desmos. All right. So now I'm going to go a distance of 2 to the right along the polar axis here, and I'm just going to continue up and down, and this is my vertical line. Okay, and now maybe you're not fully convinced that that's what these graphs look like. Maybe it kind of feels like we're cheating since we converted to rectangular and sketched the graph in polar using the rectangular equation. And what I encourage you to think about is why this equation sort of works the way it does. In other words, think about what happens as sine gets closer to 0, right? These angles out here, these smaller angles, are going to bring sine closer and closer to 0 because sine is 0 at 0 and pi. And as sine gets closer to 0, our r is going to have to get bigger and bigger in order to make the product of those two equal to 5. So as we extend this angle out further, our r gets bigger and bigger, and it does it in a proportionate way that forms this line. And a similar thing happens with cosine, because cosine is 0 at these two angles, right? Negative pi over 2 and pi over 2. So as cosine gets smaller, the value of r will have to get bigger in order to make this product equal to 2. So that is kind of a cool thing to notice, I guess. If you think that's cool, then that's awesome. But hopefully these examples make sense. Let's move on to the next couple of examples. All right, so here's our next example. We're going to look at the equation r equals 3. And essentially what this equation tells us is that no matter what theta is, our r is 3. And if that explanation in the first example helped you out, then we can do a similar thing where we write plus 0 theta. But basically, again, we're taking all the points of the form 3 theta, where theta is any angle, right? So let's see what that looks like. Let's draw our pole. Let's draw our polar axis. I'll draw a vertical line through the pole, and I'll extend the polar axis. And remember, r represents the distance from the point to the pole. So if we're considering every single angle, and no matter what the angle is, we're traveling a distance of 3 away from the pole, then really what that means is we're forming a circle. That's kind of how we define circles, is all the points that are equidistant from some center, right? So that's how we can think of this, is we can travel up 1, 2, 3, to the right 1, 2, 3, to the left, and down. So all of these points are included, but not just these points. We're taking every single angle. So let's see if I can draw a decent circle here. All of these angles, all of these angles, and all of these angles. And what this forms is a circle centered at the pole with a radius of 3. So these are actually very simple equations to graph. Anytime you see r equals some number, then it's just a circle centered at the pole with a radius of whatever that number is. And if you like converting to rectangular, you can actually do that again here by just squaring both sides and then replacing r squared with x squared plus y squared. So this is the equation of a circle centered at the origin with a radius of 3 in rectangular coordinates. So it does line up with what we have here. But hopefully that makes sense. Let's move on to a couple more examples of circles. All right, so here's our next example. We're going to graph the equation r equals 6 sine theta. And it turns out that this is also a circle, but it's not a circle that's centered at the pole. It's a circle that intersects the pole. And that's what all the circles of this form will do, is they'll intersect the pole. So to see this, I think the easiest way is to, again, convert to rectangular form. And we could start doing that by multiplying both sides of this equation by r. And what that gives me is r squared equals 6r times sine theta. And you may be thinking, why did you put the r in here? Why didn't you put it out in front? Well, I could have, but I can also move it around however I want, since this is just 3 things being multiplied. The order of it doesn't matter. So I put it there to recognize that that's equal to y, right? Y equals r sine theta. So now I can go ahead and do my conversion. On the left-hand side, we know that r squared equals x squared plus y squared. And on the right-hand side, we know that r sine theta equals y. So that gives me 6y. So now I can continue. It's starting to look like the equation of a circle, right? But I'm actually going to go further. And what I'm going to do is subtract 6y from both sides. And this is what I get when I subtract 6y from both sides. Now I'm going to go all the way back to college algebra and do something called completing the square. And what this means is that I look at this term here. I consider the coefficient, which is -6. I divide that by 2, so that's -3. And then I square it. That gives me 9, right? And that's what I add to both sides of this equation. So then if I do that, I get x squared plus y squared minus 6y plus 9 equals 9. And the reason I add this 9, the magic quality of this number, is that it allows me to factor these 3 terms into a perfect square binomial. In other words, into a binomial squared, right? Because now this factors into y minus 3 squared. And if you don't believe me, you can FOIL this out. You'll get exactly these 3 terms above. So it is, in fact, the same thing. And we still have this 9 on the other side. So now we have it in the standard form of a circle, which is typically seen as x minus h squared plus y minus k squared equals r squared, where hk is the center and r is the radius. So that means we have a center at 0, 3 and a radius of 3. So again, this information is information that applies to the rectangular coordinate system, but let's see if we can apply it to our polar coordinate system and graph this equation. So here's my polar axis. I'll draw a vertical line through the pole here. And I will extend the polar axis. So what does the point 0, 3 look like in polar coordinates? Well, in rectangular coordinates, it's on the y-axis, since my x is 0, traveling up a distance of 3. So that means it's actually going to correspond to 1, 2, 3, right there on this line. So I'll draw the point there. But this isn't a point on our graph, it's actually the center. So I'll make it red. Center will be red. It's not a point on the graph, but it is the center. And now my radius is 3. So I'm using this point and traveling a distance of 3 in every direction around, essentially, right? I'm taking all the points that are a distance of 3 away from the center. It's probably a better way of saying that. And this forms a circle, and that's exactly what the graphs look like in polar coordinates. This is the graph of this equation, r equals 6 sine theta. So a couple things I'd like to point out is that what if I change this number 6 to something else? How would that affect the information I got out at the end? Well, this number is what we end up taking half of and squaring, right? So half of this number squared always gives me this number on the right side of this final equation, which means that half of this number is always my radius, right? Because I square root this to get my radius. So half of this number is always my radius, and also the center was affected by this number as well. We're going to dive more into these patterns. I'm going to actually pull up Desmos, but once you actually learn about some of these patterns, what you're actually able to do is sketch the graph of equations like this by pretty much just looking at them. So let's hop on Desmos, and then we'll do one more example like this, where instead of doing all this algebra and completing the square and doing all that, we can just look at the equation, determine some information based on what it looks like, and then sketch the graph right there. All right, so as you can see, I'm here on Desmos.com, and if you aren't familiar with the site, I highly recommend it. I think it's a great tool, especially for learning about these polar equations, because you could just come punch in a bunch of different equations, look at their graphs, manipulate the numbers, see how the graphs change. It's a really great tool. If you do decide to come, make sure you change the grid, though. This is the default grid. Just change it so it's consistent with the polar coordinate system we're graphing in. So what I want to show in this segment of the video is talk a little bit about some patterns and some symmetries. And I talk about these in the second page of my notes, but I want to kind of show them and explain them a little bit. So first, let's make note of some symmetries. And these symmetries apply to circles that intersect the poles, so just like the example we just looked at, as well as cardioids, limacons with and without inner loops, and roses. And the pattern is that if the equation involves sine, then the graph is symmetric about this vertical line, theta equals pi over 2, or you could think of it as the y-axis, right? And let's cue some of these up and look. Here we have a cardioid. Here we have a limacon without an inner loop. Here we have a limacon with an inner loop. So all of these equations involving sine all have that symmetry about that vertical line. Even the rows. Let's see if I can cue up the rows. See that vertical symmetry. So as you can probably guess, the ones involving cosine have a symmetry about the polar axis, right? They have a symmetry about this horizontal line. And this is true for all of these equations involving cosine. Here's a cardioid. I can pull up some more. Here's a limacon without an inner loop. Limacon with an inner loop. They're all symmetric about that horizontal line. Okay, so that's something we can notice, and how that helps us is that we can look at an equation of this type and just by looking at it tell what line it's going to be symmetric about, and that could be useful when we're graphing these. So the next thing I want to talk about is a pattern, and this pattern is true for these circles that intersect the pole, cardioids, and limacons. They're not true for roses, right? But these are really helpful, especially when graphing cardioids and limacons. And what we can notice is that this pattern has to do with whether the equation involves sine or cosine, and whether its coefficient is positive or negative. So first, let's look at equations involving sine. With equations involving sine, if the coefficient is positive, then most of the graph is above this horizontal line, right? Is above the polar axis. With equations involving sine and a negative coefficient, most of it is below. And this pattern is true for cardioids as well. Look, most of it's above. This is 2 plus 2 sine theta. This is 2 minus 2 sine theta. Most of it is below. And I could pull up more examples. Hopefully you believe me by now that this is true. Okay. And another way you can think about it is the way it's oriented, right? If you want to, but I prefer to think of where most of the graph is. So this is a useful pattern that we can notice. And similarly, when we have cosine, if we have plus cosine, then most of it's to the right of this vertical line. And when we have minus cosine, most of it's to the left of this vertical line. Okay, and this is true for all of these equations involving cosine as well. Here's a cardioid. We have plus, most of it's to the right, minus, most of it's to the left, right? So this is what I'm talking about in my notes in case you were confused about what I was saying. And why this is helpful is because we can look at an equation, like let's look at this equation, r equals 2 plus 3 cosine theta. Because it has cosine involved, it's going to be symmetric about the polar axis, and because it has a positive coefficient, most of its graph is going to be to the right of the line theta equals pi over 2, right? So most of its graph is going to be over here. We're going to have some loop around here. Let's see if we're right.
See, so we can kind of get an idea in our head of what this graph looks like just by looking at it if we're able to notice these patterns. So pretty helpful. So hopefully that makes sense. We're going to definitely make use of these patterns moving forward in future examples. And as we're going to see in the next example, by using this pattern, it saves us a lot of time. All right, so hopefully this makes sense.
All right, so now that we've noticed some patterns and some symmetries, let's see if we can sketch the graph of this equation in an easier way than we did the last example like this, right? And I'm going to use what I like to call my general graphing strategy. And this is on the second page of my notes. I talk a little about it. And the first step of this strategy is essentially I look at the equation and I try to identify what kind of equation it is. And in this case, I notice that this is a circle, and it's actually a circle intersecting the pole. Right? We have two different types of circles that we deal with. The circles that are centered at the pole are of the form r equals some number. Those are very easy to graph. So this is that other type, intersecting the pole. So now that I've completed the first step, I'm going to move on to step 2, which is see how much information I can gather about this graph by just looking at this equation, right? And the first thing I notice is that this equation involves cosine. And a pattern that's true for these types of circles, as well as cardioids and Limacons, is that whenever we have cosine, the graph is going to be symmetric about the polar axis. So I'll go ahead and write that out. Symmetric about polar axis. Okay, so there's a piece of information that could help me graph this thing. What else do we notice? Well, we have a negative coefficient, and the equation involves cosine. And this is another pattern that's true for these types of circles as well as cardioids and Limacons. And that's whenever we have a negative coefficient and the equation involves cosine, most of the graph is going to be to the left of the line theta equals pi over 2. What you could think of as the y-axis, right? It's that vertical dotted line I draw through the pole. So most of the graph to the left of theta equals pi over 2. Okay, so now given this information, let's see if we can go ahead and sketch this graph. Let's see if this is enough information to sketch this graph. So I'll draw my pole and my polar axis. I'll draw a dotted line going through the polar axis, and I'll extend this as well. And now, again, we have a circle intersecting the pole. So one of our points on the circle is essentially the pole, right? It's symmetric about the polar axis, which is this line here. It's going to be symmetric about this line. And most of the graph is to the left of this line here. So since we're intersecting the pole, we're to the left, we're going to be something like this, right? And you may think, well, that's just a general sketch. I don't know anything else about this graph. And that's true. And this is when we can use some other techniques to maybe at least plot a point, like maybe plot this point, or at least maybe state the radius, right? So this is when I do one of two things. I either look at my equation and I remember the general formula, and I'm able to think, oh yeah, the radius is half this number, so the radius is 2. And if I can't remember that, then what I do is I make a table, and I do this in my notes as well, and I show how making this table can be useful. And you don't have to fill out the whole table, really just enough to help you get some points and get the information you need about this graph. So in this table, what I'm going to actually plug in is theta equals pi. I'm actually going to plug in pi. And the reason why I pick that angle is because I want to find out what this point is. Let's say I don't know by looking at this that the radius is 2. Maybe I don't have that memorized. Well, I can find the radius by finding this point and basically taking that r value and cutting it in half. That's the radius, right? And my suspicion is that the angle pi is maybe going to take me to this point, right? Hopefully I'll see why I suspect that. So let's plug in pi. Cosine of pi is -1. -4 times -1 is 4. So it does, in fact, lead us to this point, because the point r pi, we open up to the angle pi, we travel out a distance of 4. Sorry, I meant to say 4 pi. So this point is indeed 4 pi. And we do have a circle with radius 2. So again, if you have sort of these general formulas memorized, you can look at this and immediately tell it's a circle with a radius of 2. But I always want to show methods you can find this information without memorizing, because I personally don't like memorizing. So if you're like me, then you'd rather have a way that just always works without having to memorize. But hopefully this makes sense. Let's get some more practice. We're going to graph some examples of cardioids and limacons. All right, so here's our next example. And whenever we have equations like this, where we have a constant plus or minus some sine or cosine term, we're always going to end up with either a cardioid, a limacon with an inner loop, or a limacon without an inner loop. And it turns out that since these two numbers are the same, we're going to have a cardioid. That's how we can identify that this is a cardioid, because those two numbers are the same. So we're dealing with a cardioid. Since we're dealing with sine, this is going to be symmetric about theta equals pi over 2, right? Since we're dealing with sine. And we also know that most of the graph will be where? Most of graph, well, we have a negative here, right? It's minus, so that's going to tell us that this is actually going to be below the polar axis. So I'll just draw an arrow here, below polar axis. Okay, so let's see if we can use this information and sketch just a pretty rough sketch of this graph and continue from there, and then maybe gather some more information. This is typically my approach with cardioids and limacons, is gather this information, sketch the graph, and then if I need more details, I make a little table and I find out the points I need to find. So that's what we're going to do here. So since most of the graph is below the polar axis, we're symmetric about the line theta equals pi over 2. That's this line here. And if you know cardioids, then you know that they actually always intersect the pole, right? And that's actually where their dimple forms. So this little dimple is going to form at the pole, and then most of the graph is going to be below, right? Below that line, below the polar axis. So this is a general sketch, but what we can do is get some more details. We can find this point here, we can find this point here, and we can find this point here. And to do that, we can just make this little table, r theta, and let's plug in some angles. 0, let's plug in pi over 2, and I just choose these because they're very easy and quick to find. And they also happen to correspond with what I'm looking for, if you notice. This will correspond with 0, this one with pi, this one with 3 pi over 2, right? So when I plug in 0 to my equation for theta, what do I get? Well, the sine of 0 is 0, so 3 minus 0 is 3. If I plug in pi over 2, I get the sine of pi over 2 is 1, so 3 minus 3 is 0. When I plug in pi, I get the sine of pi is 0, so 3 minus 0 is 3. And when I plug in 3 pi over 2, I actually get that the sine of 3 pi over 2 is negative 1. So I end up with 3 minus negative 3. So 3 plus 3 is 6, right? And these will give me the points I'm looking for. That tells me that this is the point 3, 0. This here is the point 3 pi. And this is the point 6, 3 pi over 2. So we can get this information. We don't have to memorize all those details in that table I made or in the notes, right? Where it's like, this distance is this distance is this. We don't need to memorize all that. If we can just make this table, then it'll all work out. We can get all the information we need. Okay, so let's do a few more examples. All right, so here's our next example. It's another equation of that same form, but in this case, these numbers are not the same, right? Our constant is 3, and the coefficient of this trig expression is actually 1. We can think of there being a little invisible 1 there. So since this constant is bigger than the coefficient, we can conclude that this is a limacon without an inner loop. Limacon without inner loop. Okay, and since we have this equation involving a cosine, we can say it's symmetric. This graph will be symmetric about which line? Let's see, about the polar axis, right? Polar axis. We can also say that most of the graph will be to the right because we have a plus and cosine. Most of the graph will be to the right of that vertical line, theta equals pi over 2. Okay, so in the last example, I realized that I kind of assumed that you knew that the dimple of the cardioid would intersect with the pole, right? But if you didn't know that, I just want to say that what you could have done is you could have made that table first, plotted the points from the table, and then sketched kind of the general shape around the graph based on what you know about what a cardioid looks like, right? So we're going to actually do that in this example. It's just a slightly different order, but I just want to present this as an option and say you don't have to do it the exact way that I do it. You can go the other way, right? So first, let's do it this way. Let's find these points. Let's plot these points and then see if we can use our information to sketch the graph based on these points, right? So another order. So I'm going to plug in 0 into theta to my equation. Cosine of 0 is 1. 3 plus 1 is 4, so there's a point. If I plug in pi over 2, the cosine of pi over 2 is 0, so I just get 3. If I plug in pi, the cosine of pi is negative 1, so I get 2. And when I plug in 3 pi over 2, I get that the cosine of 3 pi over 2 is 0. 3 plus 0 is 3. So here I have some points, and I can plot these and see if I can use the information I've gathered about this graph to basically complete the sketch of the graph. Just want to offer an alternate way because maybe you don't have some of these stuff memorized, or maybe you don't feel comfortable with sketching it before you know some points. This way works as well. So we're going to go a distance of 1, 2, 3, 4. So this is our point 4, 0 right here, right? So let's consider the next point, 3 pi over 2. So I'm going to open up to pi over 2 and go a distance of 3 in this direction, so right about there. And then we have 2 pi, so that corresponds to this angle here, right? I'm opening up to this angle of pi, traveling a distance of 2. That's how I'm getting these points. Open up to the angle, travel the distance. So now 3 pi over 2 is down here, and I'm going to go a distance of 3. So now I have some points, and now I can kind of, based on what I know about how Limacons look, I can complete the sketch of this graph by just sort of sketching the shape. I know that this is going to be the dimple, and I know that most of the graph is off to the right of this vertical line. So if this is my dimple, then it's something like this, and it's symmetric, so it does this on both sides. And then this is sort of the curved end. This is the curved end, right? This kind of looks like a potato, but it's supposed to be a Limacon. Let me see if I can make it a little better. I'm not the best artist in the world. So here's our Limacon, okay? So we did it a slightly different way where we found the points first. Then we used kind of what we know about how Limacons without inner loops look to sort of fill in the rest, if that makes sense. So there's two different ways for you to do it, and then we can label these points. This is 3 pi over 2. This is 4, 0. This is 3 pi over 2. And this is 2 pi. But this still allows us to sketch the graph and get all the points and information we need without memorizing that stuff that I put in kind of the third column of the table, right? I don't personally have that stuff memorized. I typed it there for y'all to have as information, but I don't really expect anyone to memorize it. You can do it by just making a table and just knowing a few things about symmetry and patterns. So let's jump into a couple more examples. All right, so here's our next example. We're going to graph the equation y equals 2 plus 3 sine theta. And the first thing I notice about this is that it's of the form where it's either going to be a cardioid, a Limacon without an inner loop, or a Limacon with an inner loop. And since our constant term is less than the coefficient of the trig expression, it is going to be a Limacon with an inner loop. So just to kind of summarize, when the constant and the coefficient are the same, we have a cardioid. When the constant is bigger than the coefficient, then we have a Limacon without an inner loop. And when the constant is smaller, like it is in this case, we have a Limacon with an inner loop. Okay, so let's see what else we can identify about this. We have sine, so that means the graph of this equation is going to be symmetric about, let's see, which line? It's going to be that vertical line, theta equals pi over 2, right? And we can also say that most of the graph will be where? Let's see, we have a plus and we have sine, so most of the graph above polar axis. Okay, so that's some information we can gather. And again, whether you sketch this right just from this information or find the points first is really up to you. And honestly, depending on the instructions, if they're just asking for a general sketch, you can maybe even get away with not even really finding points if you're familiar enough with the idea of what these graphs look like. But I'm going to go ahead and do both. I'm going to draw a sketch and then label a few points. So here's my pole, my polar axis. I'll draw this vertical line. And now let's think about what this is going to look like. So we're going to have some inner loop here, right? So we're going to have some inner loop. And then from that inner loop, we sort of extend out. And we do that in both directions. And just warning you, I'm really bad at drawing Limacons with inner loops. So just a warning. And then we come out like this. And it looks something like this. This may be the best one I've ever drawn. So this is just the general sketch, but let's go ahead and find some points too. R, theta, let's plug in 0, let's plug in pi over 2, pi, and 3 pi over 2. Let's try those 4 angles. So when I plug in 0, the sine of 0 is 0, so I just get 2. When I plug in pi over 2, the sine of pi over 2 is 1, so I get 2 plus 3, it's 5. When I plug in pi, the sine of pi is 0, so I get 2 again. And when I plug in 3 pi over 2, the sine of 3 pi over 2 is negative 1, so I get 2 minus 3, right? So negative 1. And this is actually maybe the first time we've seen a negative r involved in one of our equations. So let's see how this corresponds to our graph. 2, 0 is going to be this point here, right? 2, 0. Let's see. 5 pi over 2, that's going to be this point up here, right? We open up to the angle of pi over 2. We go a distance of 5. That's definitely this point here. Let's see, 2 pi, that's going to be this point. And then negative 1, 3 pi over 2. So this angle is actually how we get our inner loop, because we actually end up traveling. Okay, so let me show you. Opening up to this angle of 3 pi over 2, and then going backwards a distance of 1, right? Which brings us to this point here. And that's why these inner loops form whenever we have our coefficient bigger than our constant term, is because at a certain point, we end up getting negative r values, whereas we don't get that with the cardioid or the limacon without an inner loop, right? Where here we get negative r values, which cause us to loop around within our sort of larger shape here, right? Hopefully that makes sense. So we can label this point here, let's see, I'll draw a line all the way out here, as negative 1, 3 pi over 2. And we have finished the sketch of our graph. We've labeled some pretty good points. The scaling is probably a little bit off, and that's the advantage of making the table first, is that how is this a distance of 1, but this whole thing a distance of 5? It's not really truly to scale. But again, it's just a sketch. So if you want to make the table first and have that be your method, then that's totally fine. I really doubt instructors will be super picky about scaling. As long as you draw the correct shape in the right place and label the right points, you should be good to go. Alright guys, so I apologize. This video was longer than I expected, and it also took longer than I expected. So I'm going to have to save roses for a future video, but I will be covering them in detail eventually. If that's something you want to see, stay tuned. Hopefully you enjoyed and got something out of this video or the notes I posted in the description. Any questions, leave in the comments below, and keep flexing those brain muscles. I'll see y'all later.